So what I explained last time, guys, is okay. So last time I told you about what we call a register. Register is a very important component in any digital system. So in the future, when you study computer architecture or any digital system, you will see in the system we use a lot of registers. Okay, simply because they are storage units. They are storage unit. Okay, so usually if you have like in-bit register, this register can store a number. This one number. Okay, that's why I said multiple times last time. It's one unit, one piece of data. So every bit doesn't have any meaning because it's just one piece of data. You got what I'm saying? So you store n bit, okay? And usually such a register, it has n flops, okay? And usually the way you use it, for example, if you have any circuit I explained in this course, for example, like multiplier or other or comparator, if you have any of these circuits, okay, for this circuit I need to input the data here, and then I have to get the output from this circuit. Okay, if you are doing addition, multiplication, whatever, that is why the numbers you input here, I have to store it somewhere, and usually what we do, use register. The output here I have to store it somewhere, and usually we store them in registers. Okay, and usually what happens, this data here, usually either it comes from memory, so I can read the memory, store it in the register, or this data may be coming from the user. So you are asking the user, please give me a number. You get the number from the user, you store it here. After I set the two registers, now I can tell the multiplier or the other, do the addition. You can notice we have steps here, okay? And that's what you should notice when you study any computer architecture. You can see we have steps. If I want to add two numbers, okay, one number coming from the user, one number coming from the memory. So number one, I have to get the first number for memory. This may take multiple cycles from the clock, and then put it here. Number two, okay, I have to put the second number here. When these two numbers are already there, now I can give a command to do the multiplier to do the addition. What I'm saying? Once this is done, the output will be here. Maybe I want to store the result in the memory back. You got what I'm saying? So it's like you have steps here. Anyway, so that's what I explained last time. So I explained here how can we create a register, normal register like this one, and then I improved it last time by adding just this little part in order to have a control on how or at what. So here I just added here what we call a load, okay? So that if load is 0, that means I'm not going to allow the input to be stored here, okay? But if the load is 1, so now I have a control at what time or when I want to. So you have some data here, but this data is not going to input, is not going to be stored here until two things happens. Number one, load is 1. Number two, there is a clock. So it has to be two things. Okay, clock alone is not enough, but I have to put a command here. I have to put one here. Okay. Anyway, so I explained this one, and then I moved to a second type of registers. We call it shift register. Shift register. So shift register means if you have a register, you are storing a certain number, for example, 1101, something like that. So I can shift. So shift means, for example, you have some input here. For example, I'm going to input 0. Then when there is 1 o'clock, at 1 o'clock, so every bit here is going to be moved to one position. Okay. And this, I'm going to input a new bit. Then I'm going to get rid of one bit, and the other bits are shifted. So after 1 o'clock should be 0, 1, 0, 0, 1. So let me here. Yeah, so it should be 0. This one should be 0. This one should be 1. So it's shifted from here to here. Okay. And this one should be 0 and then 1. This one is gone. Okay. Same thing. So every clock you do one shift. And I told you this is shifted to the right. Okay, you can have another shift to the left. Yes, you can design the circuit to work this way, and that's what I explained here. The way I can do shift right is very simple. Look, very simple. All what you have to do is the output of circuit of one flip-flop is input for the second one. Okay, so if you see what happens here is when there is a clock, so here is this one, A3 is gonna move to here because this flip-flop is gonna store the input. Okay, so this one becomes A3, this one becomes E2. Is that okay? And this one becomes E1, right? And then the input is gonna come to here. So you can see the shift is done to the right. Is that okay? I can just switch the circuit so that shift can be done to the left. It's the same circuit here. Okay, so in the future, that's what I'm saying, guys. So we are in the last week. I told you the purpose of this course is not, that's why it's called Introduction to Digital System. It's not to teach a system, but I'm teaching here the main components I'm going to use in a system. So in the future, when I create a system, I'm going to tell you I'm going to use a shift register, but I'm not going to explain to you what is shift register. You got what I'm saying? Because these pieces, you have a pieces here. We didn't create a system, okay? We just have pieces in this course. But in other courses, we are going to take these pieces and then create a system, digital system. Is that okay? So this is one of the pieces, shift register. I told you we can do shift register to the left, so it can move this way. So all what you have to do, very simple. So this one becomes D, this is Q, D and the Q. D here and the Q here. So you just switch D and the Q, okay? And then the input come from here, the output from here, okay? Very simple. So every clock, the data is shifted. So you input one bit. So here, what happens here? Here you have you have here the input here in D, the input is gonna come to here. This one here is gonna jump to here. This is what was here is gonna jump to here. What was here, jump to here. You got what I'm saying? So every bit is gonna be shifted one step to the left. Okay? Also, I told you here about something like rotate. This is also one of the operation we do. Rotate right, or also we have rotate left. So as you see here in rotate, I'm gonna take the last bit here. I'm gonna input it here. So I'm not gonna input a new bit. So this is, if you look at this circuit and you compare it to this circuit here, it's exactly the same thing. It's exactly the same thing. However, I'm not gonna input a new one. Okay, so this input is gonna come from here. Okay. So that's why it's called recirculate. You just circulate the bits. I'm not going to input a new bit. Anyway, so you can see I just circulate here. Okay. And this is, again, you may wonder how this is useful. Yes, it is useful, but I can't tell you now. But because when you take like you read a system, you may need something like that. Okay. So like you rotate the bits this way. Okay? Every clock. So every clock, as you see here, this bit comes to here and everything shifted to the left. So you're not going to input any new bits. You're not going to lose any bits. You just rotate them. Okay. That means after 4 o'clock, you're going to get the same number back. Look here. This is 1. After 4 o'clock, I get the same number because I rotated all of them. Okay. Anyway, and then also last time, I told you about something like very important, like serial communication and parallel communication. So also that's what I want to, that's also what I explained last time. For example, if you have 4-bit data, just an example, if you have 4-bit data, I want to transfer it from point A to point B. Usually we have 2 ways to do it. The first way, you call it a parallel transmission. So what happens here, I have to connect 4 wires because I have 4-bit data. Okay. And then what's going to happen, I'm going to just put my data here, just 1, 1, 0, 1, whatever. And then I need only 1 clock. After 1 clock, so this data is going to be received here by at this site here. Okay. So it's for sure, it's very fast because all we need only 1 clock, and then you are going to transmit everything. Okay. For example, 4-bit here, this way. We have another type of communication. We call it serial communication. Serial. So in serial communication, we have only 1 wire. So here, this is a transmitter, this is a receiver. So we have only 1 wire here. And the way it works is, we have here like 1101, for example. This is the number I want to transfer. So what happens here, after 1 clock, so this number has to come to here, and then here I'm going to get 1. Second clock, so I'm going to get this one here and transmit 1. Next clock, I'm going to transmit 0. Next clock, I'm going to transmit 1. That means I need 4 4 clocks. Every clock I'm going to transmit only 1 bit. Okay, so you can. It's very easy to observe that this one is just slow because you're going to transmit bit by bit. But here I transmit 4 by 4. Okay. So anyway, so this one is slow. This one is fast. However, the good thing about this one, we need only 1 wire. You get what I'm saying? And it is useful. It is used when you learn something like I2C or microcontroller, things like that. You will see this one is used. Okay. USB, by the way, our USB is serial. Okay. So it is used, and this is the most important thing. And in order to implement something like that, I need to do here at this site here, I need to do parallel to serial conversion. Here, I want to do here, what I want to do here, serial to parallel conversion. So that means I'm going to receive bit by bit, but after that, it becomes parallel. So the way you can do this one simply is, or actually both of them, you can just use shift registers to do that. So here, if I have a shift register this way, every time I receive 1 bit, I'm going to input it here. Is that okay? After 4 clocks, I can take the numbers here parallel from here after 4 clocks. You get what I'm saying? So every clock, I'm going to shift 1 bit. After 4 o'clock, now I have the number, I can take it in parallel. So same thing here, but it's going to be a little bit different. So what I'm going to do here, I'm gonna output bit by bit this way. So still shift register, but I'm going to upload the number parallel load. So now I have a number. So for example, 1101. Okay. So this number, I'm going to just parallel load. I'm going to put the number here. Okay. This number on number 2, and then every shift register. So this one is going to output 1 by 1 this way. Is that okay? You understand what I'm saying here? This is how shift register can help us. They can help us to do something like parallel to serial conversion or serial to parallel conversion. Any questions? Okay, so that's what I explained to before. Today also I'm going to explain something somehow interesting to you. Sometimes it's not only in communication, sometimes in some operations. So here, sometimes in operations, we can do operation in 2 different ways, either parallel or we do it serial. Okay, so I'm going to give you more details what I mean right now. Okay, and then I'm going to give you one example to understand better what I mean. For example, if you remember in chapter 4, we designed a parallel adder. So what we did here, we designed an adder. Okay, so this, for example, 4-bit adder. And in the 4-bit adder here, I'm going to input 2 numbers. They are 4-bit here and 4-bit here. And then I'm going to get the output. Okay, so I do the addition at the same time. So here 4-bit and 4-bit, and I can do the addition at the same time. This is parallel. Now I can do the same thing here in this operation, but I'm going to do it serial. So that's what I'm going to explain. How can we do that? How also shift register is going to help me to do that. Okay, but you should understand what is the difference between parallel and serial. In parallel, I need the complete number here. I need the complete number here, and then I do the addition. I get the complete number here. In serial, I'm gonna get bit by bit. You get what I'm saying? So I'm gonna show you how shift register can help me to do that, and this is what I'm explaining here. Yeah. So if you look at this circuit here, what happens here is, here I have only 1 full adder. I have only 1 full, and this is the interesting part. Okay, I have only 1 full adder. So this full adder, it should have 3 inputs. 2 inputs are coming from 2 registers. So this register is storing number A and number B. So I have two shift register. Every register is storing 1 number. One number. This is the 2 numbers I want to add. Every shift, you are going to get only 1 bit here and 1 bit here. Is that okay? Let me complete. And then also here, the output here is going to be sum and the carry. And then I'm going to use a flip-flop here to store the carry. Why? Because I need this carry in the next bit addition. So that's exactly what happens here. When I add bit to bit, I'm going to get a carry, but I need to keep this carry. Why? Because when I add the next 2 bits, I'm going to use the carry here. So the carry resulted from the first 2 bits, okay? And also, okay, and the output I'm getting here, I can store it in a separate register so that I have a number here A, I have number here B, and then every shift, I'm gonna get 1 bit here, 1 bit here, I do addition, and then the result is stored in a different register. You can do that. Or the way I did it here is the summation, which is the result of adding bit to bit, is gonna be shifted back to A here. It's gonna be shifted to A. So that means it's this one is gonna do like A should equal A plus B. So this is A and this is B. Is that okay? This is number A and number B. Shift register, shift register. Is that okay? After, for example, if this shift register is 4 bits, this one 4 bits, I need 4 clocks. Every clock, I'm gonna add 1 bit from here plus 1 bit from here plus the carry resulted from the last operation. Okay. And then once you do that, the result I'm gonna feed, because this is shift register, the result of him, I'm gonna feed it here. Is that okay? Again, you can design this way, or you can store the result in a different register. But usually in computer systems, usually you do something like that. A should equal A plus B. So you put a number here, you put a number here. After 4 clocks, you are gonna get the result of the summation here. What about the old number that was here? It is gone because A should equal A plus B. Okay, I made some videos to make it just easy for you to understand how it works. For example, assuming register A is storing this number, register B is storing this number. Okay, let's see how it works here. So what happens here in one clock, I'm gonna add these 2 bits together. Okay, and then for originally this one I have to clear this, or initially in the very beginning, I have to clear this flip-flop so that I get 0 here, because the first carry here has to be 0, right? So the first carry here has to be 0, okay? But the carry resulted from here, from adding these 2, is gonna be stored in the flip-flop here. This one stored in the flip-flop and so on, okay? So what you can see here is, because this is a shift register, so here, I'm having here 1, we're having 0 here, and then I have 0 coming from here. If you do the addition, the result is 1, and the carry is 0. Is that okay? Then after the first clock, so I need 1 clock. After the first clock, this 0 is gonna start here because I need it in the next 2-bit addition. And this one, which is a part of the result, is gonna come here. This one is gone, so I'm gonna shift. So these 2 are gone. So that's exactly what I'm showing here. So what I'm showing here, what happened if you compare this one with this one, okay? So after 1 shift, this one is gone, this one is gone. Now this bit is out, now this bit is out. Now this bit here is gonna be shifted to here. And now this carry resulted from adding the first 2 bits is gonna come here, okay? That's it, as you see here, okay? So this is the first bit of the result. I got the first bit of the result, okay? Then after, so now I have this one here, I have this one here, and then I have 0 here, okay? So now I'm doing this addition here, okay? So every clock, at every clock, I'm gonna do this one, another clock here, another clock here, another clock here. That's why I'm saying 4 clock, okay? So every time you shift, you take only bit and bit, add them together with the carry, then you add the carry. Anyway, so then the result here is 0, the result is 1, and then I need to wait for a clock until this one comes here, and until this 0 is going to be shifted here, okay? So that's why I need, after 2 clocks, now after 2 clocks, I got 2 bits of the result. And now this one is here, this one is here, and the carry, the last carry was 1, so now I'm doing this one here, okay? And then the result is 0 and 1, but this result is not stored yet, so I need a clock. After a third clock, so every clock I'm gonna get only 1 bit of the result, okay? So you see here. So finally, after 1 more clock, so here you have 1 and 0, okay? Now I'm doing this addition here, okay? And this is the result here, but I need 1 clock to insert it here. So you can see here, after 4 clocks, you can see this is the result I got, and this is the carry I got. We can see it is exactly similar to the result I have here. Okay, very interesting. So let's make it very simple. What I'm explaining now, guys, I want to do a certain operation. What I'm explaining, like addition, for example. What I'm explaining, I can do this addition in a parallel way. And that's what, if you go back to chapter 4, that's what we did in chapter 4. I have to input 4 bits, I have to input 4 bits, and then you do the addition, okay? So this one is going to be very fast. Is what we did in chapter 4, very fast. However, we needed 4 flip-flops. You need more hardware, right? So we need 4 flip-flops. Sorry, 4 others. I'm sorry. Chapter 4 doesn't have flip-flops. We need 4 others. Okay, 4 full others. But here I'm going to use only one full other, only one. What I'm saying? But this one for sure it is slow. It's slow because here I need 4 clocks, 4 cycles of the clock in order to get the whole addition. And the idea is that because I'm using shift register here, every clock I'm going to shift 1 bit. So, okay, as I explained, and then you add these 2 bits here, you shift the result back to here, okay? So here, this one, you can have less hardware because you need only 1 flip-flop, but it is slow because you need 4 clocks to do it, okay? Again, I just want to give you some idea, just in case in the future, you see something like, I'm going to do this operation in parallel, or I want to do this operation in serial. Also, this is also, you can see here, this is like an application for shift register. How can you use shift register? So again, the idea is that every shift, I'm going to get one bit. I'm using here only 1 flip-flop, 1 flip-flop. Even if you add, even if you're adding 100 bits plus 100 bits, because it's still 1 flip-flop. This is the interesting part, but it's slow, right? Because you are gonna, every clock you shift 1 bit, you do the addition, you store the carry here because you need the carry next time, okay? And then you need to store the result somewhere, you store it here, okay? Anyway, one interesting thing here I did not explain yet. So let me tell you, so as you see from the conclusion here, every clock, what happens here, every clock you shift here, you shift to the right, every clock here you shift to the right, every clock, the result from here, I insert it here, okay? The carry resulted from, I'm gonna store it here so that I can use it next time here, okay? And that's why I'm telling you this A and B, and after 4 clocks, A should equal A plus B. So the way it has to work, I have to put number here, I have to put number here, and then after 4 clocks, A should equal A plus B. Is that okay? There is one more thing that's really very interesting, okay? Is also, we have serial input here. We have serial input here. So how this one can be used for? Okay, I'm gonna tell you. If you have something like running addition, for example, here, I wanna add number plus number plus number plus number, okay? So what I can do, I can take the first number here, I can put it here in the very beginning, and then I take the second one here, I put it here in the very beginning, okay? And then every shift, I'm gonna shift 1 bit from here. Shift 1 bit here. So that after 4 clocks, what I'm gonna get here, A plus B, or the first 2 numbers, for example, I'm gonna say here, I'm gonna call this one, for example, N1, number 1, number 2, number 3, number 4. So in the very beginning, you have to put number 1 here, you have to put number 2 here, okay? And then after 4 clocks, what's gonna happen is that after 4 clocks, I'm gonna have here N1 plus N2. Also, I'm gonna have here N3. N3 is gonna be here. Why? Because every time I shift N3, I'm gonna connect it here. So every time I shift to do the addition of N1 plus N2, what's gonna happen is that, very interesting, what's gonna happen is that the summation, bit by bit, you are gonna input it from here, bit by bit. Same thing, the new number, I'm gonna input it here bit by bit. So that's why after 4 clocks, I'm gonna have here N1 plus N2, and then I'm gonna have N3 here. After another 4 clocks, I'm gonna have here N1 plus N2 plus N3, and then I'm gonna have N4 here. You got what I'm saying? Because I'm gonna shift every time you shift, I'm gonna insert. You are gonna output 1 bit from here, you output 1 bit, and then I'm gonna input 1 bit from the new number. So it's gonna be like having like running addition. Any questions? Anyway, so what I want you to learn here, guys, number one, this is just one application for the use of shift register. This is number one. Number two, you should understand something, an operation. I already explained how can we do communication in parallel and in serial. So you should understand the difference between them. And when you do communication in serial, this is also another application for the use of shift registers. Okay. Also, what I'm explaining here, if I have an operation like addition, I can do it in two different ways. If you go to chapter 4, I did it in parallel. Okay. Here I'm doing it in serial. Okay. So here you add bit by bit. So in serial, the good thing about serial, I need only one flip-flop, only one. Okay. Even if the two numbers, even if I'm adding 1 billion bit to 1 billion bit, it's still one flip-flop. Very interesting. Okay. So it's good for hardware. It's gonna be cheap, but for sure it's gonna be slow, because every clock I'm gonna add bit to bit. That means if this one is 8 bits and 8 bits, to finish the addition, I need 8 clocks to get the addition. Okay. In parallel, it's gonna be faster. You can get the result just in 1 clock or quickly, but you need, if I add 1 billion bits, for example, to 1 billion bits, you are not going to need to do that. I just want to explain the concept or the main idea. If you want to add too many bits to too many bits, so for every bit, I need one flip-flop. Okay. So if you add 60 bits to 60 bits, so that means I need 60, and you want to do it in a parallel way, I need 60 flip-flops to 60 flip-flops. So it's going to be very bad for hardware. Any questions? Any questions? Okay, so here, nothing is new here. I'm gonna show you now. So what I explained so far, guys, number one, we can have, you can have what I explained so far is I can have a register, and if I have a register, I can do shift left, or I can do shift right. Okay, shift right, shift left, or you can do parallel load. Parallel load. So parallel load means, for example, I have 1 1 0 1 0. When you do parallel loads, just I need 1 clock, is going to be 1 0 1 0. So you upload in parallel. And if you shift, you actually is going to give you bit by bit. So I can get bit by bit from starting from the most significant bit. If you do left, if I do right, so I'm going to get bit by bit from here. I'm going to get bit by bit. But if you do shift right, that's what I explained. Is that okay? Okay. Now I'm going to do something interesting. Nothing is new, but I'm going to do something interesting now. We have something we call universal shift register. Okay. Sometimes you can find a chip. This chip has a universal shift register. Is that okay? So this shift register can actually do the three operations here. So as you see here, for this chip, or I'm gonna design it right now, you can see we have here selector, as you see here. So I have 2-bit selector here. So if I put here 0 0, that means no change. So if this register is storing 1 1 1 1, it's gonna stay 1 1 1, no change. If it is 0 0, okay. But if I make it like 1 and then 0, okay. So actually this one is gonna act like shift right. And if I make the selector 1 0 this way, so this one actually is gonna act like shift left. If I make 1 1, so this one can do parallel loading. Okay. That is why you can see here. Okay, that is why you can see here, we have here 4-bit. We assume this one is 4-bit. For sure, 4-bit register. For sure, when you buy a chip, it may be more than that. But anyway, so here, I'm gonna design a circuit for 4-bit. You can see here, we have 4 bits here. Sometimes we do it this way. So when I put backslash this way and say 4, that means this one actually 4 bits. Okay, so instead of just making it 4 this way, so I'm make slash this one and tell you this is 4. Okay, So here, this one is going to be used for parallel load. So if you are in the parallel load here mode, if you are in this mode and you have a this number is going to stored here 4 bits. Okay. Also, we have here, we have serial. So this is in case of shift left. So you can input bits from here and bit. Okay. You can input bits from here. And in case of if you shift right, this is input here. So I'm going to choose a circuit here. So again, what I want to say, nothing is new here. All what I'm going to do, what I explained to you before regarding shift left, shift right, parallel load, I'm going to put all of them in one circuit. Is that okay? And you have selector here. And you will see, we will see right now, I didn't do anything new. I just put everything in one chip. And the reason I'm explaining it, just in the future, if you need to use a chip that has universal shift register, so at least you know what I mean by universal shift register. So I'm going to show how it looks like. So if you it looks so complicated, no, it's not. I'm going to tell you how it works. Okay, so if you see here, because this one is 4 bits, so have 4 registers. Every register should store 1 bit. Okay, all of them have the same clock. So you can see all of them are connected to the same clock here. All the clear pin is connected to all of them. That means if I put here 0, I clear all of them. All of them are connected to the same clock. The only difference, is, again, this one should do one of 4 things. No change, shift left, shift right, okay, parallel load, one of 4 things. Okay. The difference between the 4 things, where is the input has to come from? Where is this input has to come from? That is why I'm using a multiplexer here. This multiplexer has selector S0 and S1, okay? And the 4 multiplexer have the same selector. So if I select here number 0, I select here 0, I select here 0, I select 0, because all the selectors are connected together. If I select here 1, I put 1, and put 1, okay? And this is how it works. The way it works is, again, this register should do one of 4 things. The difference between them is where is the input has to come from. So let's start with the first one here. If I put 0, 0, that means should be no change. No change means if it is storing 1, 1, 0, 0, it should continue 1, 1, 0, 0. So in this case, as you know, from multiplexers, if the input here is 0, 0, so you actually are going to connect pin number 0 to the output. That means the D here, the input of the flip-flop is going to be connected to pin number 0. Is that okay? Okay. How I can make no change? So what should happen is that to make no change, okay, all what I know, if I put here 0, 0, so the input here is going to be connected to pin number 0. We agree on that. Is that okay? So the question is that, what should I put here in pin number 0 in order to make no change? You got the point? So what I have to do here, I have to get the same number here. I put the same number here. So what I did, I connected. If this one is storing 1, I'm going to put here 1. So that when the clock comes, I'm going to stay 1, as you see here. So here, if you put 0, 0, I'm going to connect a bit 0. And in order to make no change, I have to connect this pin 0 to the output of the same output here. You got it? That's why I can make no change. Any questions? Let's see another one. Now, if I put 1, 0, so I have to make shift right. Shift right. Shift right means it has to move this way. Shift right. Okay. Very simple. If you put here 1, 0, that means that all the multiplexers are connected to pin number 1. Pin number 1, pin number 1, pin number 1. Okay. So the question is, what should I put here in pin number 1 in order to make shift right? What should I do? Very simple. To make shift right means, so here A3 has to come to here. That's why I'm going to connect this one to A3 to make shift right. So here, every output here has to be connected to the next one. Okay, so that's why I connected here. Let me use a different color. Whatever, let me, for example, use this one. So you can see here. Okay. So you can see here, all of them are connected to pin number 1. Okay. So in order to make shift right, so I have to take A3. This A3 has to be connected to the input of the next one. So that's to go to A1. And this one here has to go to here. Okay. This one here, A1 has to go to the next one here. And the first one here has to come from the serial input. You got it? So that when the clock comes, I'm going to store here the serial input. I'm going to store here A3. So A3 is going to move to here. I'm going to store here A2 and so on. Okay. Very simple. So here it's just how I wired it, in order to give me shift right when the output here is selected from number 1. Okay. Let's see one more. Now, if it is 1, 0, so it has to make shift left. In case of shift left, they have to move this way. In case of shift left, is that okay? So if this is number 2, so I know that the input of each flip-flop is connected to pin number 2 or input number 2. So the question is, in order to make shift left, what should I connect here? What should I connect at pin number 2? Okay, very simple, because it has to move this way. So I have to connect here. For this one, I have to connect E0. So E0 has to come to here, right? E1 has to come here. E2 has to come to here in order to move them this way. Okay. And serial input for the first one has to get the serial input because I input from here and everyone shifted to the left. Okay. Okay. Let's see next one. Next one, if you make 1, 1, so it has to be parallel load. What parallel load means? I have 4 bits in the input. I just want to store the 4 bit directly here. And this is, as you see here, if I put 1, 1, multiplexer is going to connect every input here of flip-flop here to number 3, number 3, number 3, number 3. So the question is, what should I connect at number 3 in order to make parallel load? Okay. So very simple. This is the parallel input. This is the number I want to store. Okay. So yeah, this one has to connect it. So I have 4-bit number. And once here you have 1, 1. So these 4-bit numbers are already connected here to G and G and G. Okay. Again, several things you can learn here, guys. Number 1, at least you can see a very useful application for multiplexer here. Look how multiplexer can help me to create a circuit like this. Okay. Number 2, nothing is new here. What I did, I put 4 circuits. I already explained before. I put them in one circuit. Got what I'm saying? And I can select which circuit you want to connect using the selector you have here. Is that okay? So one chip, you can buy this. You can buy it as a chip. This chip can do. This chip can do 1 of 4 things based on what you are going to select in the control here. Any questions? Good. So I am done with registers. Okay. I am done with shift registers. I told you we can do shift right. We can do shift left. Here in register, we can do parallel. Parallel load. You have a number. Just I can store the number. Just in one clock, store the whole number. That's what we call parallel load. Here we have hardware circuit to do shift register. Even I explained to you why this shift register is important. We use them actually, especially in serial communication, because serial communication are widely used. So when you learn the microcontrollers, you can find some circuits in microcontrollers are serial. Okay, so that's why shift register are widely used for that. Okay. Now the next two parts here. I want to move to counters. So number 1, we have 2 types of counters. I'm gonna explain. One is called rebel counter. The other one is called synchronous counter. So first, let me make a definition. What do you mean by a counter? What counter mean? Okay, that's what I'm gonna tell you now. So counter means, before I give you hardware circuit, how can you do it? And then I'm gonna tell you a surprise now. The surprise is we have already done counters. Number 1, the generator you met in the project is a counter. Number 2, In chapter 4, in chapter 6, in chapter 5, there was an example, how can you make a counter, okay? So let me first make the definition, and then I'm gonna come to this one. So let's make a definition. The definition of a counter is, you have a hardware circuit, okay? A hardware circuit. This hardware circuit should have clock, okay? And then, for example, assuming here I'm gonna make 3-bit counter. Again, guys, please, when I say 3-bit counter, it doesn't mean all counters have to be 3-bit. This is something I can design. I can make it 7, I can make 9 by just adding one flip-flop. That's it. So here I give just one example. Same thing for other. I give you one example for other for 4 bits, but that doesn't mean all others have to be 4 bits. No, this is design. This is something you can design. You can make 7, 8, whatever. You understand what I'm saying? So you can design it. But I just give you example for a certain number. So here I'm explaining 3-bit counter, okay? So if you have 3-bit counters, number one, you have a clock this way, you have a circuit here, whatever the circuit is, that's what I'm gonna explain. How can you create this circuit? And then I have 3 bits here. I have 3 bits here. Is that okay? Because it's 3-bit counter. If it is 4-bit counter, I should have four outputs here. Okay. And then this is how it should look like. Okay. Actually, we have two types of them. We have one of them is called count up. I'm gonna talk about this one first. So in case of count up is, if you look at the output here, I'm gonna call it ABC, whatever it is. So ABC. So if you look at the output here, you can find it is number 0 in binary, 0, 0, 0. Okay. And then after one clock, okay, it is actually, you can see it number 1. So this one has to change to number 1. After one clock, you can see this number in binary, number 2. After one clock, you can see this one is number 3, and then number 4, then number 5, okay, and then number 6, and then number 7. Okay, so every clock, the count you have incremented by 1. Okay, then after 7, you are gonna go back to 0, 0 again. So it's like you are gonna go back to count again from 0, 0. If again, I'm just making a definition. What is a counter? Okay, so a counter, it has an input here. This input, for example, it can be a clock, and for every clock, the number here is going to be incremented by 1 in binary. Okay, so that's why here I have 0, then I have number 1, number 2, number 3 in binary, 4, 5, every clock. Once it comes to 0, it's going to go back to 0. Once it comes to 1, 1, 1, 1, it's going to come to 0, 0 again. This is a definition. What is counter? Is that okay? Okay. So if you, that's what we call a counter. This is if it is count up. We have another one that count down. But before I continue, in the future, how can I use a counter like this one in the future? Again, as I told you in this course, I'm explaining something, I call it a counter. But how can you use it in the future? That's what you are going to learn in the future. But I just can give you some idea right now. Listen to me. It's very useful. We're going to use it all the time in digital systems. Okay. Number one, for example, the input here doesn't need to be a clock. The input here, for example, I want to count. I can put like a sensor here, infrared. So I can put something like this is infrared light here. Okay. I want to count, for example, you have some cars here. So every time a car is gonna cut, this line here, the infrared light. And then when you cut the line, this sensor is gonna generate a pulse. So if I connect this pulse here, if you connect these pulses here, so now what I'm doing is I'm counting how many cars crossed the road, for example, or how many if it is application for a persons entering a store. So I can, every time you cut the line here, you trigger a pulse. Is a hardware sensor is gonna do that, and this one is gonna count. Okay, so this is one way to use it. One way to use it if you want to count some events. You got what I'm saying? It's the same idea here. I can use it to measure the speed of a motor. But anyway, it's maybe, so in the future, you will get something like that. If you have a motor, this way, usually I put the disk this way, and the disk, for example, I put two holes here, and then I put here like infrared, something like exactly same thing here, so that in every rotation, every time the motor makes up one complete rotation, you are going to generate 2 pulses here. Okay, so you are going to count here. So the number you are going to get here, you have to divide it by 2. You get what I'm saying, to get the number of revolutions or number of rotations, something like that. Okay, so this is one way I can use it this way. There is another way to use it, this hardware circuit. I can use it in a different way, and this time I'm gonna call it a timer. Usually timer and counter almost the same thing. The difference, I'm gonna tell you what is the difference. So this time I'm gonna call it a timer. Listen to me. Again, this is something you are gonna learn in the future. I don't care much about it, but I just want to give you some idea how this can be useful. Here in this course, I want to focus on the hardware, how I can make hardware to do something like that. That's what I mean focus. But if I connect here something like a clock is this way, so this one becomes like a timer. What you can tell from the English name timer. Timer means you can use it to measure time. Time, right? You measure time, timer, right? Yes, because if you see here, every clock, for example, here the time is T. The time for one clock is T, okay? Every clock is gonna increment the count by 1, okay? So if I wanna measure time, for example, if I have a pulse like this one, I want to measure the time from here to here. This is something you should learn in other courses, okay? So I want to measure the time from here to here. The way usually we do it, I can see what was the count here and what was the count here. For example, if I start here at count number 3, and here it was count number 7, what it means? It means from here to here, the timer counted 4 times. 4 times. And because the time of each count is fixed, is T. That means from here to here, it took 4T. So I use it to measure things this way. Anyway, so I can, regardless, this is something I don't want to spend more time on that. This is something, let's focus on the, how can I make circuit like this one? So I want to make a circuit to behave this way, okay? So I told you we have count up, also we have count down. Sometimes in some application in digital systems, I want to make count down instead of count up. So let's start so here in count up, every clock, you increment the count by 1. Is that okay? And I can design the circuit, and that's what you will see right now. I can design the circuit to make count down. So what count down means? It's the same thing, but instead of incrementing the count by 1 at every clock, I'm going to decrement it by 1. You get what I'm saying? That means here, count down. So here I'm going to start from 1, 1, 1, which is number 7. So after 1 clock, it should be number 6, because every time you decrement, you don't increment, you decrement by 1. So it has to be 6. Okay. Now, after 1 more clock, it has to be number 5. Is that okay? Which is 101. So it has to be all the way until 0, 0, 0. Okay, so every time you decrement by 1. When you come to 0, 0 and you decrement by 1, you are going to come to 1, 1, 1, 1, 1 again. Okay, so again, I can design a circuit to increment by 1 every time we have a clock. I can design a circuit to decrement by 1. That's called count up and count down. Again, both of them are used in digital systems. Okay, so in the future, in any course in the future you take, the instructor is going to do, we are going to use count up counter or count down counter. You should know what is this. Okay, so now let's come how we are going to design it. Okay, we're going to number 1, as I told you, we already did it before. We designed before in a difficult way. The difficult way. Now I'm going to do it the easier way. Okay, so I'm going to tell you what is the difference between easier and difficult. We did the difficult way. The difficult way is, this is a sequential circuit. So you need to draw the sequential, the state diagram, and then design the circuit. This is what you did in the project in the generator part. That's what you did. This is exactly same thing we did here. If you go to, I'm going to show to you where in chapter 5 we did that. So if I come to chapter 5, yeah, we did it here. So if you see here, this is a counter. Look, what happens here in every clock, you start from here. Sorry. Yeah, so you can see here, I start from number 0. After 1 clock becomes 1, 2, 3, 4, 5, 6, 7, and so on. Okay, so you can move in a certain sequence this way. Okay, so you can do this way, and then you can design the circuit. It becomes something like that. Okay, maybe this is a difficult way. So you can do this way using, as we did before, sequential circuit. Now I'm going to tell you, okay, I don't need to do it in difficult ways. This one, I'm going to do it in a much easier way. How? I'm going to tell you how. You get what I'm saying? So what I'm saying, I can design counter this way, like what we did here, but this is a difficult way. I have another way, which is just an easier way. Why is going to be easier? Because I'm going to show it now. I'm going to have an observation, and then I'm going to use this observation to design it. So you will see right now how I'm going to do it. But okay. So here in this chapter, I'm going to explain. So here, I'm going to explain two types of counters. One is called rebel counter. The other one is called synchronous counter. So what is the difference? They are just two different ways. Again, every time you see the word synchronous, what it means? It means all of them have the same clock. That's the meaning of synchronous. So number one, you should understand, guys, is if you want to make n-bit counter, so actually you need n flip-flops. Is that okay? Make it easy, n flip-flops. So the question is that here in case of synchronous counters, so the n flip-flop I have, the clock, their clock are connected to the same, that they are going to be triggered by the same clock. That's why it's called synchronous here. So here in these circuits, both of them are doing the same thing. Both of them are counters, but the design will be different. I can design in two different ways. One way to connect the same clock to all of them, that's why it's called synchronous. Okay. In rebel, every flip-flop is gonna trigger the next one. So the clock of one flip-flop should come from the output of the previous one. You got what I'm saying? This is the main difference. So here, if you have a flip-flop this way, so the output here is gonna go to the clock of the next one. Same thing, the output here is gonna trigger the next one. So that's why you use the word rebel. You can see some kind of rebel effect here. Everyone is gonna impact the next one. Okay. So anyway, so I'm gonna explain to you how they work. I'm gonna show you how they are very easy. Then I'm gonna tell you why they're easy to design. But for now, you should understand what is the difference between them. One of them, you have clock connected to the same clock is connected to all of them. That's why it's called synchronous. In case of rebel, the output of flip-flop is connected to the input of the next one. So this one is triggered from the previous flip-flop. This one is triggered from the previous flip. So let's start with rebel first, okay? So if you can understand this observation, everything will be easy after that. So let's start. We have an observation here, and then I'm going to show you how I'm going to use this observation to design the counter without making sequential. It's actually sequential circuit, but what I mean, without making a state diagram or a state table, if you understand the observation here, okay? So let's look at the very important observation here, because this will help me to do the design, okay? So what is the observation here? Look here, guys. First of all, this is how the counter should behave in order to get a counter. If you look here, guys, 0, 0, 0 for one clock, okay, which is number 0. So you can see here I have 0, 0, 0, 0. So this is the timing diagram for counter. Any counter, if I have a count up 4-bit counter, this should be the timing diagram. So I'm going to start from the timing diagram. I'm going to investigate the timing diagram to get an observation. Then I'm going to use this observation to do the design. You will see it's a very simple observation here, but let me finish here. So this is how the timing diagram should be if you want to make 4-bit count up. Okay, so here you have 0, 0, 0 for one clock, and then here you have 1, 1, 0, 0, which is number 1, and then you have here 0, 1, 0, 0, which is number 2, and then you have here 0, 0, 1, which is you have, I forget 3. You have 1, 1, 0, which is number 3, until number 15, which is 1, 1, 1, and then after that we should get 0, 0 again. So if you look, this is just, nothing is new. if this is a counter, it has to behave this way, because every clock, every one clock, you are going to have a number. So number 0, number 1 for 1 clock, number 2 for 1 clock, number 3, number 4, 5, 6, 7 until 15. After 15, I'm going to get 0 again, because this is 4-bit. In case of 4-bit, you can count from 0 to 15. Is that okay? If it is 5 bits, you can count from 0 until 31, and so on. Okay. Anyway, so again, nothing is new. Just if this is a counter, it has to behave this way. There should be, this is a timing diagram. Okay, okay. Now I'm gonna have a very important observation that's gonna help me to design the counter. Look at the observation here. Remember, every flip-flop has to trigger the next one. That means that here I should have 4 flip-flops. This is 1 flip-flop, 1 flip-flop, 1 flip-flop. So I have 4-bit means I have 4 flip-flops, okay? So the flip-flop here has to be triggered from the output of this one. The flip-flop here has to trigger from the previous one. So everyone has to be triggered from the previous one. So let's see the observation we have here. So okay, what about the first one? The first one should be triggered from the clock. This is how the rebel counter is. So in a rebel counter, I have a clock. This clock should be connected to should trigger the first flip-flop, which is E0. Then the output of this one has to trigger next one. The output here has to trigger the next one, and so on. Is that okay? This is the definition. This is a rebel counter. Okay. So now look at the very interesting observation. Look here, because A0 is triggered by the clock. Look here. What is the relation between clock and A0? What is the relation? The relation is every time there is a falling edge here, A0 has to toggle. Again, the clock is connected to the flip-flop of E0, right? So look at what is the relation between clock and E0. The relation is every time there is a falling edge here, E0 has to toggle. Right? Just an observation. It's going to help me to design. Okay. Now, because E1 is triggered by E0, this is a rebel counter. Every flop is triggered by the previous one. E1 is triggered by E0. Look at what observation you can have here. The observation is every time there is a falling edge here, E0 has to toggle. In order to get this timing diagram, falling edge, toggle, 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 falling edge, toggle. Look at E3. E3 is triggered by E1. Look at what observation we have here. Every time there is a falling edge, toggle, falling edge, toggle, falling edge, toggle, falling edge, toggle. What about E3? E3 is triggered by E2. Look at what I'm saying? So, same thing, the same observation. Every time there is a falling edge, this one has to toggle. It's an observation, right? In order to get this timing diagram, okay? The first one here has to toggle at every falling edge from the clock. This one has to toggle at every falling edge from this one. This one has to toggle at every falling edge from this one, and so on. How I can do it? Very trivial. All what I'm gonna do is I need to make a flip-flop that toggle at every clock. So I have to select the input. I have to select the input of the flip-flop to toggle every clock. How I can do that? Very trivial. So if you are using T flip-flop, so here at T, I have to put 1. And then I put a clock here. That's it. So if you have a clock, if I put here T flip-flop, if I put 1, I put clock. So this one, every time there is a falling edge coming from because I'm going to connect the clock to E1, E0 here. Okay. So every time this one is going to toggle every time there is a falling edge. So the way I can do it here, I can make 1 flip-flop here. I can make T, then I'm going to fix it to 1, connect the clock here. Same thing here. I can make both T here. I can put 1, and then the output here is going to be connected to the clock here. Same thing here. So this one, every time they connect the output here to here, T is 1. Same thing here. T is 1. The output here is going to be connected here. So I have flip-flops. I'm going to select the input of the flip-flop to toggle. Every time there is a clock. Every time there is a falling edge. That's why every time there is a falling edge, this one toggle. Every time there is a falling edge from this one is going to toggle because I'm going to connect this one to the clock of this one. Same thing for others. So to do that, if you want to use T flip-flop, I can simply, for T, I can put 1. Okay. Can anybody tell me if I want to use J key flip-flop, what should I do? If I use J key flip-flop, what should I do? Connect them together to 1, right? Yes. This is how I can make it toggling. Connect J to K, connect it to 1, toggling. Okay. What about D flip-flop? Anyone can tell me what should I do for D flip-flop to make it toggling? How I make D flip-flop toggle? Every clock it toggles. Anyone can tell me? You have something to say? What is that? Yes. No, I'm going to make it easier. Look here. I have Q and I have Q prime. I'm going to connect Q prime to here. You got what I'm saying? So I have here. This is the output and this is the inverter of the output. So if this is 1, this is 0. So I'm going to connect this one to here. That's why I can make this one toggling. So every clock, this one is going to toggle. Okay. Anyway, so it's very simple. So I'm going to repeat it again. If you want to make a flip-flop that toggle at each clock, all what I have to do is just, if it is T, put 1. If it is JK, connect them together and put 1. If it is D flip-flop, you have to connect it to Q prime. So every clock is going to toggle. Okay, and that's exactly just by this observation. I don't need a sequential circuit. I don't need to design it is a sequential circuit, but I don't need to make like a state diagram, state table, and all this difficult. You know, for counter, I can make it just. I have observation here, so I'm gonna have 4 flip-flops that are toggle every time there is a falling edge, and then I'm gonna connect the clock to trigger this one. This one is gonna trigger this one. This one is gonna trigger this one. This one is gonna trigger this one. By this way, I can get this timing diagram. Look how it is easy, right? So that's why you can see the circuit. Yeah, that's why I have the circuit here. For example, yeah, that's exactly what I'm explaining. For example, if I use T flip-flop, as you see here, I just here I connect 1, 1, 1, 1. So all of them are toggling. And then the count or the clock here is connected to the first one, E0. The output here is connected to toggle this one. The output here is gonna toggle this one. The output here is gonna toggle this one. Is that okay? So everyone is going to toggle next one. And all of them are in the toggle or complement mode. So any one of them can complement, right? Let me ask you a question. So for example, I designed here 4-bit. In exams, if I tell you in the exam, can you make a 3-bit? Yes, just delete 1, remove 1. That's very simple. If I tell you, make it 6-bit counter, yeah, just to connect here 2 more. That's it. You got what I'm saying? Okay, here it's the same thing, exactly same thing, but what I did here, I just connected Q prime, I connected to Q prime to D. Everything else is the same. So the clock is connected here, the output here is connected here, the output here is connected here, the output here is connected here. Any questions? Any questions? Again, you should understand the observation I have here because I built the design based on this observation. Is that okay? Okay. This is how can you make count up. What about if I want to make count down? Very easy. Also, I'm going to have observation here. If I want to, here this time I want to make count down. So here, as you see, I want to start from number 15. After 15, I get 14, 13, 12 until 0. After 0 should be 15. So every clock, I'm going to count down, decrement by 1. Is that okay? So how can we do it? Again, I will try to get also an again, you can create a state diagram. You can make a state diagram, and then you can design it similar to what we did in chapter 5. The other thing you can do, you can just get an observation here for this is, if this is count down counter, this should be the timing diagram. It has to behave this way. You can see here number 15. And then number, if for every one clock should be decremented by 1, decremented, it has to be this way. And then I'm gonna get an observation. This observation should help me to design it easily. Look at the observation here. You can see this one has to look, because this, again, because this is a rebel counter, very easy. In case of rebel counter, this one should trigger this flip-flop. This one here, the signal has to trigger this one. This one has to trigger this one. This one has to trigger this one. So that's why to design it, I need to know what is the relation between these two. Also, I want to know what is the relation between these two. Also, what I want to know the relation between these two and the relation between these two. Okay? So let's see, look here. You can have an observation. This is the observation can help me. So look at the observation here. So I can see here, every time, look, every time there is a falling edge here from the clock, every time there is a falling edge from the clock, this one has to toggle. Falling edge, toggle, falling edge, toggle, 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 toggle. So that means E0, as I'm writing here, E0 should toggle at every falling edge of the clock. This is an observation. Look at E1. What is the relation between E1 and E2? Because E2 is gonna be the clock for E1. It's gonna trigger E1. This rebel. Okay. So look at the observation here. The observation here. Every time we have a rising, not falling, rising, toggle, rising, toggle, rising, toggle. Okay. What is relation between E1 is gonna trigger E2? So what is the relation? It's the same thing. Rising here, toggle, rising, toggle. Same thing between E3 and E2. Rising, toggle, rising, toggle. Is that okay? This is just an observation. So if I can make a circuit this way, if I can make a circuit, number one, all the flip-flops are toggling. So I'm gonna make them, I'm gonna make the input so that every clock they toggle. Okay, that's number one. Number two, this one has to toggle at falling from this one. This one has to toggle at rising of the previous one. Toggle at rising of the previous one. Toggle at rising of the previous one. Is that okay? But there is a small problem here. What is the small problem? Okay. It's not a problem, but usually, so there is a very easy way to do it. The very easy way, because you know, if I have a flip-flop, I can have a flip-flop that is, this one is gonna toggle at rising. And then I can make another flip-flop that toggle at falling. I can use this way. So I can use, this one has to be here because this one has to toggle at, sorry, this one has to be at falling. So I can use here, this one has to toggle at, but this one has to toggle at rising. So I can use the easy way to do it. I can use two different types of flip-flops because I can see this flip-flop has to toggle at falling, but this one has to toggle at rising. So I can use two different types of flip-flops. This is one way to do it. Usually, we don't like it to do it this way. If you want to do it this way, it should be okay. However, usually we like that all of them have the same type. You got what I'm saying? So look how I'm gonna do it. So all of them is gonna be triggered at falling, all of them. But how? Because this one has to be not at falling, not rising. Okay. Look what I'm gonna do. So here, the way I can do it here. So I'm gonna use 4 flip-flops. This number one. All of them at falling. Okay. And then this one can be connected directly here without any problem, right? Because I wanted this one to toggle at falling. So just connect this one. There is no problem. Is that okay? Okay. But if I take E0 here and connected it here, that is wrong. Because if I do this way, the next one is gonna toggle at falling. But what I wanna do here, this one has to toggle, okay, at rising, not falling. You know what I can do? Very simple trick, okay? What I can do is, I'm not gonna connect it to E0. I'm gonna connect it to E0 dash here. So this one should be okay. So here that means this one here is not gonna be triggered by E0. It's gonna be triggered by E0 prime. And E0 prime, every rising here is gonna be falling. I flip, because remember, every flip-flop is gonna give you E0 and E0 prime. It's a complement of this one. So you have this signal, E0. I don't know, I can't use this one. because this flip-flop triggered at falling. I want to trigger it at rising. So what I'm going to do is, instead of taking E0, I'm going to take E0 prime. So in E0 prime, actually what will happen is, so this one will be 0, this one will be high, and then this one will be high. Look here, this one rising is going to become falling. Maybe I want to draw it. Let me draw it here. You got what I'm saying? So every rising here in prime is going to be falling. So this will do what? So it's going to be here. Yeah. So here, because it is just the inverter. So if this one is rising, it becomes, I'm saying I made a mistake. So this one here, yeah, 0, this one high, okay? This one is gonna become 0. I just flip it, okay? So here rising becomes falling, and that's exactly what I did. Very simple. So what I did here, guys, that's exactly what I explained. For the first one, I just connect the clock directly to the first one, because I want the first one to toggle at falling. So this one should be okay. But because everyone after that should toggle at rising, you have two options. Either you connect it you can connect it to Q directly, but this time you have to use a different type of flip-flops, which triggered at rising, or I can keep it triggered at falling, but this time I'm going to connect it to prime. Q prime, Q prime, Q prime. Any questions? So here I use T flip-flop. I connect to one here. So this one can toggle every time. Any question here? The next thing I want to explain here is something we call it BCD counter, just in case in the future you see it. In case I just want you to know it. BCD counter. You remember, as I told you, in BCD numbers, we have numbers from 0 until 9, right? This is BCD, right? That's what I explained in the first lecture, first few lectures, BCD. So now, if I want to use this counter, so in this case, I need to use 4 bits. 4 bits. However, what we did before, if I use 4 bits should count from 0 until 15, and then 0 to 15, and so on. But I want to count here BCD. What it means? It means still I need 4 bits, but I have to cut here at 9. So it has to count from 0 to 9, and then 0 to 9, and then 0 to 9. Is that okay? So I'm going to use 4 bits, but still I need to use 4 bits, okay? However, I'm not going to count from 0 to 15. No, 0 to 9, and then 0 to 9, 0 to 9, and so on. Is that okay? Again, there are 2 ways to do it. You already have a state diagram here. So this should be the state diagram. I start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 should be 0 again. So you can start from the state diagram. You can make a state table, and then you can design the circuit, because this is sequential circuit, similar to what we did before. Okay? But I'm not going to do this way, because this chapter here, I want to focus on, sometimes we can do it in a very simple way, some tricks. Similar to the tricks I explained right now, just if you look at the falling edges or timing diagram. So now, what I'm going to do it somehow in a different way. Look what I'm going to do. What I'm going to do is, again, you can do this way. You can just go and design like a sequential circuit as we did before. You can do this way, okay? But I'm going to do it in a simple way. So what I'm going to do is, I'm going to use 4-bit counter. Okay, look here, 4-bit counter. But once I come to number 10, I need to reset all flip-flops. You got what I'm saying? So I'm going to use the same circuit for 4-bit counter, but I'm going to make a trick, or I'm going to add a circuit, a combinational circuit, so that once it becomes 10, I'm going to reset all of them. Okay, that's it. So here, and that's what I did here. So what I did here to design this one is, this is without this part. If I just cancel this part here, this becomes like 4-bit counter. As I explained before, you can see I connect J and K connected to 1, 1. So they are toggling. and then the output of one is input to the next one. So this is exactly what I have just give me 1 second. This is exactly what everything I explained before. However, look here, look, this is the trick I made. I'm gonna connect the reset. All the reset are connected together to a NAND, and this NAND is actually connected to here and here. Okay, so that if this one is 1 and this one is 1, the output of the NAND becomes 0. And this once this one 0, so I'm gonna reset all of them. And actually, this one is here is gonna become 1 and 1 when the number is 10. So in case of number 10, yeah. So here, once the number is 10, okay. So you have here 1 and 1, and this 1 and 1 should come here 1 and 1. Output is 0, so that you reset. So I'm gonna force you are gonna count 0, 1, 2, 3, 4, 9. Once you come to 10, it's not gonna continue. I'm gonna force the flip-flop to reset this way. Any questions? Yeah. So as you see here, it's connected to the second bit. So it has to be 0, 1, 0, 1. I'm sorry, the other way. It has to be 0. It has to be 0, 1, 0, 1. So this is number 8, this number 2. So once I have 1 here and once I have 1 here, I'm gonna force the flip-flop to reset. You get what I'm saying? So it is the same 4-bit counter I explained to you before, but I did a small trick so that once I have this number, it's gonna okay. You can just twist this idea a little bit. What if I want to counter that count, for example, from 0 to 11 for some reason, and then after 11, 0 again? Very simple. Or what you have, I can use the same idea here. So this one can count from 0 to 15, and then I can force this one once it becomes 11 to reset all the flip-flops. Any questions? Okay, thanks.